Alright, welcome to the next episode of my tutorial series. This time we will be talking about how to pull that frame that you built last time into the simulator module, and we'll be able to apply some loads to it. So first thing you want to do is open back into that file by double clicking on it. And while it's loading here, I want to mention a couple things. Remember we talked about how we'd have to put in the straight lines for it to work. And that is because this is actually a beam model. So what that means is it's not actually splitting this geometry into individual little mesh. It's actually going to treat the entire thing like a beam, and it's going to propagate the cross-sectional areas the same way you would in like a statics or a mech of solids class. But it's obviously going to do those calculations in 3 dimensions and for whatever loads you apply. So that being said, that leaves you with a couple advantages and disadvantages. The big advantage of that is that you're going to be a lot less likely to have meshing issues, and the meshing issues that you do have are usually easier to fix and happen faster because it's not a super fine mesh. And then those same advantages are also a disadvantage because your results may not be quite as accurate. Although, you know, when you're building with steel tube, as long as you've got a decent factor of safety, it's a pretty well documented process and building medium. So I wouldn't be too afraid of using these results and leaning on them with some reliability. Okay, so to enter the frame analysis, we're going to go here to, you can either go under design or environments. The stress analysis is where you do the analysis on like a solid model. Maybe I'll talk about that in a future episode. I've never used the Inventor one, but I've used other types. But we're going to be using the frame analysis today, and obviously you have to have a frame already built. So first thing you have to do is click Create Simulation. We're going to call this Torsional Rigidity Study 1. Okay, and we want it to be a static analysis because we're not looking at vibration modes, although that's something you could do apparently. I'm not too familiar with how to do that. We're going to leave everything as a default. If you wanted to do different positions or different levels of details, that's something you could do, but at this point we're just going to go with it the way it is. So then it's going to collect all your section properties. And again, like I said, it's going to turn into a beam model. So again, here you can see why we put in the straight sections instead of the curved beams. If you have curved beams in your model, it will just ignore them. They won't be there. It took me a little while to figure out why my model was behaving really weirdly until I figured out that it was just completely ignoring them. So yeah, this is why you need the straight line sections. And again, you could essentially imitate a finer mesh by doing maybe 4 or even 5 sections here, but for now we're just going to go with 3 for the sake of simplicity. You know, making 3 or 4 or 5 or 6 wouldn't really be that hard. Okay, next thing, materials. Very, very, very important. Make sure that you have these set to exactly to whatever you're using. Back in the other Inventor space, you can change everything at the same time. So say you've got an error here. This one will show up red. That's a really common error. One thing you can do is you can click Customize, and just within the simulation, this won't change your model, but you can go down here and you can use this drop-down menu to change what the model is recording, or what the simulation treats it as. So say I wanted this, say I wanted this to be plastic. I could go turn it into ABS plastic, and that would only apply to this simulation and not to the actual model. Obviously, I'm not going to do that. But because I don't have any red blocks here, we're good to move on to the next step. However, if you were having an issue and you needed to just make everything all one material, I can go up here, or say I wanted to change it and I realized I did it wrong. I can go under here. I'm going to go and see if I can find 4130 steel. Doesn't appear to be in here though. I'm going to go to the Autodesk material library, which is a little more in-depth, and choose 4130 steel, because that is the one that we tend to use around the shop. And I will apply that. I think now everything should be a 4130 steel. So again, all I did there was I had make sure the whole thing was selected, applied the material, went to materials, see all the members are highlighting, and then I double clicked on the material that I wanted. 4130, we'll do that again. I don't know if it applied or not. This does take some fussing around. It's not always the most cooperative. So now we got to add it to our document. And just to check, we can click on it and it will, okay, so it's still generic. Maybe I can, yeah, okay. There's a way to do this. I'm not exactly the best at it, clearly. I've had some issues with this in the past. Oh, assign to selection, there we go. So you can right click and go assign to selection, and then it should actually make them all. So if you go to edit with frame generator, should be 4130. Yeah, you can see it's now 4130. Okay. So yeah, that's what you have to do. You have to go into the frame, click it once, click it once, go to repeat material, or even just like you can open up the material browser in any way. As long as you have it selected, have the material browser open, right click the material you want, assign to selection, and then your selection will become that. Okay, so now that we've got that out of the way, that's a good way to just make sure that automatically everything's the material you want, particularly if your frame is all one material. Okay, now we'll go back to environments, frame analysis. I can now go to material, and I can see that, so I have to make sure that it's updated. Oh, why did it not update? Let's create another simulation. Let's call it torsional rigidity simulation 2. Okay, so sometimes you can see some of these errors here. These are just white and yellow errors, so I'm going to ignore them for now. I know this is not necessarily the most sound advice. It says the torsional section modulus is 0 for the square tube. Not sure why that's the case or how to fix it, so I'm just going to ignore it for now. And you can see that now I have the correct material properties in here. Yeah, I'm not really sure about that error, but we'll see if they have some crazy problem in the results, then I guess we'll go from there. Okay, so this is where we get to applying constraints. So so you've got all sorts of constraints. You've got fixed, pinned, floating, and custom, where you can fix it in whatever axes you want. You can also apply. You also can apply displacements, I believe, and you can also apply rotation. But for now, we're just going to use fixed in all directions, and we're going to apply that to each of these nodes at the back of the chassis here. Oop. Fixed. Yeah, I want the offset to be 0, right? Okay. And you do have to, you can hold down control to apply it to multiple ones if I remember correctly. Oh, maybe it's shift. The reason I'm not too familiar with this is because I really only set it up once or twice for each study, and then I really only varied the loads and the geometries. So basically what you're going to notice that I do is you'll set these constraints, and then once you're done setting your constraints, you can apply any sort of load you want. So your options are going to be a force at a node. So for example, or you can apply it along an axis, I guess. Or no, this will apply a point load anywhere along that axis. If you want a distributed load, then you can apply that using the continuous load. And then your other option, of course, would be a moment. You can also do an axial moment or a bending moment. So if you wanted to apply a bending moment along the whole tube, you could do that. I do not want to do that in this case. You can also apply an axial moment if I wanted to apply a moment to that tube. But the one we're going to use here is just the regular node moment. And what we're going to do is we're going to torque the whole front of the frame. So I actually want it to twist that way. So we're going to apply, let's say 500 foot-pounds at each node. I'm just completely coming up with these numbers out of nowhere. While I'm putting these in real life, you'd want to do some serious research and think about what your load would be in real life. What I mean by that is, if you're looking to see how this chassis performs in torsion, you want to use a load that's the angle. You'd want to use a load that similarly represents what it would be seeing in the real life. So for example, you'd want to talk to your suspension guy about the types of suspension loads that it would be seeing. And he'll be able to calculate those from some even just some napkin calculations, or whatever they call it. You could probably get some values that would be in the ballpark here. Now you don't need to use any loads that are in the exact, like, down to a tenth, because you're going to be more concerned with the actual loads that are being seen in your chassis and how they perform relative to each other. As long as you've got some factor of safety, it's not going to be too important that you get some exact load. So it's more important that you spend your time as the simulation guy, trying to get as much simulation data as you can, and trying to get a couple different geometry configurations, or maybe tube wall configurations, wall tube thickness configurations, than it is that you need the exact weight value down to a tenth of a second. Okay, one more to go here. And we're going to drag that 90, make sure it's still 500. Okay, so now I'm just going to apply a continuous load here. Let's try 100 per foot. Okay. Ooh. Looks like it's at a bit of an angle. I didn't know you could do that. Most of my experience comes with... Oh, it looks like you can set a starting and an ending magnitude. So we'll set those to be the same. Okay, so again, like, you could probably say for now this was just the middle part of your chassis where the driver sits. You could apply a road, some moments that roughly equate to the torsion of that would simulate the car in maximum braking and turning, or something like that, at the most grip the tire could provide. But once you built the chassis out and you've got actual suspension points, I would recommend asking your suspension guy to calculate what those exact loads would look like, and that will allow you to be a little more accurate. So I'm going to go ahead and click simulate here. It'll take a moment to go through it. I have a reasonably powerful computer. It's not anything super special, but it's able to crank through it pretty quickly. Failed to get results. Prohibited use of a support in slave node number 11. Okay. So we're going to go here under node. You can also look at all your nodes and all your beams here. So for example, it's saying I have an issue at node number 11. I kind of put down the supports rather odd. So I think what I'm going to do is I'm going to go ahead and delete all the supports and then try to get them re-going here. Delete. All right, so we're going to try those again. Fixed. I'm going to click on a node. Check. So I think what happens is if you accidentally click on the beam, it'll ask you for the offset you want. But what I prefer to do is try to get it on the actual node itself. It tends to like that more, although it doesn't really want to let me do that here. So we'll just go ahead and do it on the beams. As you can probably tell, I'm not exactly a simulation expert, and this is not exactly the highest end simulation tool. But at the end of the day, it's really, you know, miles better than nothing. You're informing your design based off of a simulation. It may not be the most accurate, but you know, I'm also talking about trying to get ballpark loads. But you know, what you got to think about is the optimization of these parts relative to each other should still be pretty good. Okay, it still doesn't like the way I'm doing this. Nodes 9 and 11. Can I find in window? It didn't like the way I did this. Maybe I can just fix the center beam in the bottom. You know, I'm not going to be too worried about not fixing this corner because I'm pretty confident that that these top ones and that constraint in the middle will hold it pretty well. So let's try that. There you go. Okay. So again, you know, it's a little bit of finicky. Play around with it, see what the best you can do, and you know, maybe once this works, then maybe go try it back and do it again the other way. But for the sake of making the video, we'll treat this as though it's good enough for the moment. Okay. So when you initially load and click simulate, it will primarily just spit out the displacement as your initial contour plot. They call it a contour plot. It can be a little confusing, but all that means is that it's just you know, showing whatever these units are here on top of your frame. This can be a little hard to read, but this says displacement and this says inches. So the red, we're seeing 150 thousandths or 157 thousandths of displacement, and it goes down to 0. So if we go into results here, we can look at a whole bunch more stuff. We can actually look at the axial load along the things. We can see that the maximum we have here is almost 2,000 pounds. We can look at moments along these in all 3 dimensions. And the most important one, in my opinion, is the stresses. S-max will show you kind of the essentially what is the places where you have the highest stress concentrations and what beams are being stressed. So for example, you can see here that the stress along this front hoop is actually distributed pretty evenly and is not really much higher than doesn't seem like it gets out of anything more than a light green here, which is like 25 at most. And if I'm not mistaken, this metal doesn't fail until we're in KSI here. So let's just Google something real quick. You know, shear modulus of 4130 steel. So we're not failing until 11,000 KSI, and we're only at 78 here. So we're doing pretty good. We're not anywhere near. So for example, if these were our rough suspension loads, we could go way down in tube thickness or even tube wall size. You know, some of the if some of these were dictated by rules, we could potentially go down. But we'll talk more about kind of how to interpret these results in the next video. For now, let's just focus on the thing itself. I think that's really about it. This is a pretty straightforward thing. Oh yeah, real quick, let's talk about you can do probes. So one thing you do, you can display a min and a max value. So for example, it's actually showing my max value there and my min value there. And it will do the same for displacement. So I go back to displacement here. It'll show me where my maximum displacement occurs. This is really useful for stress, pointing out where stress concentrations are occurring. I can also put a probe. So say I want to probe. say I want to know what's going on at this top shoulder bar, we'll call it, in roughly there. I click OK, and now it will show me whatever I'm looking for here. So in this case, maximum stress. It will show me what the stress is at that point. So now, if I wanted to, and what I'd advise you to do is, leave these markers as you change simulation variables and you do your studies, so you kind of have a couple reference points. So pick a couple key areas that are really important, and take some data down for that. We'll talk more about that next time, but this is kind of the screen that you'd take screenshots off of if you wanted to visually represent to somebody what was going on. You may or may not want to leave on the boundary conditions. It's a little cleaner to look at, but it's also, if you're just looking at it for the first time, you may not know what's going on. So that is up to you. Oh, also, one thing to point out that I had forgotten about. Let's go back here to loads. By default, it turns on gravity. So say I actually, it's not anything significant, but you can also, if it's like not a very significant value if you're looking at pretty large loads on steel. So I might actually suppress that. Now you can see that this gets a red lightning bolt by it. That means that the results that are already in there are no longer valid and we need to recalculate. But while we're at it here, I'm going to try to fix my constraints. So I'm going to turn back on the boundary conditions on the display tab here. Which one is in the middle there? So that's fixed constraint 1. So we're going to go ahead and delete that and see if we can't get a better fixed support going on here. Okay, let's click check and try it again. We'll go to simulate again, see if it throws us that same error. Yeah, it's throwing the same error still. I wonder if this is a similar issue that I was having while I was doing it on the actual chassis, and I'll talk about the actual simulation that I have set up potentially in a future episode. But I'm honestly not sure why it's doing that. The Autodesk Forums are really helpful, so you could copy paste that error message into a Google search and have a lot of luck. I've had a lot of luck, specifically searching error messages. It'll say, oh, here's what you need to do. So that's something worth considering. I'm trying to think if there's anything else that I've used. I think this was one of the things that I actually messed with to get that error to go away, but I do not exactly recall what that was. I will leave you with that for now. In the next video, hopefully we'll talk about kind of how to record and how to analyze some of the results here. I know I mentioned a couple brief things, but kind of how to make a presentation that's pretty easy to look at can be a little bit difficult, particularly when we're looking at these pretty crazy graphs that are not always very obvious what's going on for somebody who was not working on them. So we'll talk about how to do that in the next video. Okay. All right, just a quick note here. I was able to get all these constraints to work. What I ended up doing is I just clicked the nodes. Basically what happens is when you trim these beams, it actually will trim them down. And so you can see that blue line doesn't extend all the way down into the node there. But what it does is it joins them all into one big node, basically using, it kind of treats them as one big node within the beam model. But for some reason it didn't like having both those supports down there. I'm not exactly sure why, but it let me put them on the slightly higher node at the end of this beam. But one thing I will point out though is it does make a huge difference not having that one support in the middle. So it's little things like that you can kind of help a not so accurate simulation tool be a little bit better by kind of fighting with it a little bit and making sure that you get your load case as good as you can. before we were looking at 157 thousandths, we're now looking at 47 or 48 thousandths maximum displacement. So little things like that do make a difference.